A storage engine like Bitcast is well suited for situations where the value for each key is updated frequently. For example, it might be the URL of a cut video and the value might be the number of times it has been played, incremented every time someone hits the play button. In this kind of workload, there are a lot of writes, but there are not too many distinct keys. You have a large number of writes per key, but it's feasible to keep all keys in memory. So you have a lot of keys, but uh, you have few keys, but you have a lot of updates. This is where it shines, as discussed in the previous video. As described so far, you only ever append to a file. So how do we avoid eventually running out of disk space? A good solution is to break the log into segments of certain size by closing a segment file when it reaches a certain size and making subsequent writes to a new segment file. So since we're not deleting anything, we're only appending to the disk. One of the good strategy that people have invented or did is to actually break the log segments up to a certain size. Usually it's just 3 to 4. Once you usually get to the keys, to the right keys in 3 to 5 segments. In real world, you usually have 5 to 7 segments, and you rarely go as far as that. We can then perform compaction on these segments as illustrated in figure 3.2. So once we create this, for example, 3 to 7 segments, we can now perform a compaction to remove or to prune it. Figure 3.2, compaction of a key value update log, counting the number of times each cut video was played, retaining only the most recent value for each key. So as you can see, we only retain the value for the most recent value for each key. Compaction means throwing away duplicate keys in the log and keeping only the most recent update for each key. So in compaction, since we only ever append the data, these segments, and we only have 3 to 5, this compaction happens asynchronously using a background thread, using a one thread, usually just a one thread to avoid concurrency issue. And then this one thread will perform it, and since it's only a few segments, 3 to 7 segments, it is able to do it efficiently. Moreover, since compaction often makes segments much smaller, assuming that a key is overwritten several times on average within one segment, so because once you do the compaction, let's say you have 7 segments, all of the duplicates there and not recent keys will be removed, because remember, we're dealing with few keys but a lot of update data. Now those will be removed, and we can also merge several segments together at the same time as performing the compaction like this. So as you can see, we have compaction and merging. Performing compaction and segment merging simultaneously. So for merging, since we have prune data on a segment, we may be, some segments have doesn't have enough data in it, so that's the reason we also merge it. And of course, merging still run using our programming language. Segments are never modified after they have been written, so the merged segment is written to a new file. So since we're only ever appending on it, we're not overwriting really into the disk. This merged segment is actually written to a new file. So we combine this already prune. So of course we do the compaction first before we do the merging, because we can efficiently merge a segment if we were able to compact it first. What's the confusing part? You read segments are never modified after they have been written. And at the same time, the key is overwritten several times on average within one segment. And your brain says, how can something be overwritten if segments are never modified? Key clarification, nothing is ever overwritten on disk, but the logical meaning of a key is overwritten by newer entries appended after it. So the logical meaning, such as the new merge file segment, the prune, after we compact it and prune the duplicates, that's the new logical meaning. So overwritten here means overwritten in meaning, not overwritten in place. Imagine Bitcast like a notebook. A segment file equal one notebook. Writing values means you never erase old pages. You just keep writing new pages. If a key updates, you write page 1, video A equal to 1, page 20, video A equal to 2, page 57, video A equal to 3. So inside one notebook segment, the key video A appears many times. All values still physically exist, but only the last value matters. So key overwritten logically. File ever modified? No. What is compaction? Compaction equals tearing out useless old pages and keeping only the latest version per key. So the compacted file contains video A equal 3, video B equal 7, video C equal 2. This creates a new segment file. The old segment file is deleted later. This is why they say segments are never modified after being written. Correct, because instead of modifying them, we create new merged ones and delete old ones. Why do some segments shrink after compaction? Because inside the segment, a key appears many times. Only the last entry matters, so compaction removes duplicate. Meaning key is overwritten several times on average within a segment. Key has multiple updates, multiple log entries. Compaction deletes them except the newest. So that's what that sentence means, since we're dealing with update heavy workload and multiple log entries. And during compaction, you remove the duplicate. It means it is overwritten several times on average within a segment. How this relate to everything we've been discussing? Firestore storage before. Firestore internally is also a log structured storage system similar to idea to Bitcask, RocksDB, LevelDB, meaning writes append, segments get compacted, keys logically override previous keys, segments are immutable, compaction merges plus delete old ones. So a compaction, remember, we didn't just compact or remove duplicate keys. We also merge it to create a new segment to a new file. So yes, even in compaction state, still binary structures, still protobuf encoded, just rewritten into new segments. This is why Firestore is fast at writes, crash safe, great for append workloads. IndexedDB local cache in Firestore Web SDK. Our earlier question, who enables listeners to resume when offline and reload? Answer, Firestore Web SDK mirrors query results into IndexedDB. So the Firestore Web SDK mirrors the query results from Firestore into IndexedDB. IndexedDB behaves similarly, stores snapshots, keep latest values, doesn't mutate in place. It is only appended syncs when online again. So index DB equal your local segment. Firestore server equal remote segment storage. So think of IndexedDB as your local segment. So it's still a segment, but it's just a local. Sync process equal background compaction plus merge. So the sync process in browser is a compaction first and then merge. LiveKit and WebRTC metadata question. Does LiveKit metadata touch Firestore before screen sharing? Connecting to this discussion, WebRTC Media never touches Firestore. Only metadata does. Metadata writes act like log records. If metadata changes repeatedly, same key overwritten logically, stored in protobuf binary exactly, like these logs. So the metadata of LiveKit still use the Firestore log records. So if it changes, it's only appended and is stored in protobuf binary exactly like these logs. So yes, it's the same architectural philosophy. Where does abstraction end? Abstraction ends where actual storage engines write immutable segments, background threads merge plus compact. Clients only see latest logical value. So you stop in the actual details of how they store the immutable segments and the background threads, merge plus compact. So how the actual what's the actual code of Firestore of merging plus compacting? It's actually private. Clients only see the latest logical value. So in your meta stack, React or Next.js to Firestore Web SDK, to IndexedDB Mirror Cache, to Firestore Backend, to log structured segment files, to compaction or merge or delete, to disk SSD. Every layer follows the same pattern. Append, version, merge, retain latest. Final simple truth, there is no contradiction. Segments are never modified. Keys are overwritten logically. Overwrite means new entry supersedes old entry. Compactions removes old entries in a new file. Old files are deleted after switching. So how does it relate to OS 3CP? I watched some YouTube video that oversimplifying how the code actually controlled the hardware. So he has a case that it only used memory map IO, but it's actually there is more than that. So think of it like this. In OS 3 AC pieces, it explains how programs see and use memory, virtual memory, paging, protection. Memory map IO explains how hardware gets wired into that same memory space. So when the CPU writes to memory, it may actually be talking to a device. So in OS 3 easy pieces, you talk to memory, but sometimes you also talk to memory map IO. So inside those physical address memory lies the memory map IO. So it's just part of this, of how the program actually interact with the hardware. So your program, OS virtual memory abstraction, then MMU translation, then physical address space. We have RAM chips, GPU register, network card registers, SSD controller registers, other device registers via memory map IO. So this is where the memory map IO. And then after that, there's another abstraction, which is electricity modes, and then hardware reacts. Memory map IO literally sits beside RAM in the physical address space, not conceptually above it. Like APIs or OS abstractions, That's the aha, the video hit me. So does not mean three easy pieces is the real world explanation. It explains half of reality, how the OS makes memory look simple to software. It does not deeply describe how devices are exposed as memory. So it doesn't explain the driver, of course, there's a details on that. It doesn't explain the electricity, of course, so because that's another abstraction, but a lot of it is actually from OS. If you understand OS alone, you would understand the hardware better or the other easily. But if you don't understand OS, it you will have a hard time understanding the how it actually works in reality. So that memory map I always simplistic, though it got a lot of views. OSTEP touches devices in device driver chapters, but not deeply. Where memory map IO normally is covered, you were right, it is usually in CPU architecture books. It's actually is inside the machine, so that will complete your knowledge of how the hardware actually works or the CPU architecture. Inside the machine does talk about system buses, address decoding, device registers, physical versus address spaces. So that book is closer to where MMIO lives. Other common places it's taught, embedded system books, computer organization or digital logic courses, write your own OS resources, ARM or times 86 architecture manuals. Why your brain felt foggy even after reading all those books. Totally normal, and honestly, this is a great sign. Here's why. Most software books stop before the electrical boundary. Books like OSTEP, Data Intensive Apps, TCP or IP Illustrated, Full Stack Web About Face explain software abstractions, processes, threads, networking stacks, databases, UX, distributed system. They deal with complex systems built on top of the hardware illusion. They don't normally go all the way to bus lines, address decoders, memory map registers, CPU execution pipeline, MMU versus bus fabric. So it's common to feel like I understood computers until I look one level deeper. That means your curiosity moved past the abstraction boundary most programmers live inside. A cleaner mental hierarchy, let's teach everything. Level 5, product or UX work, about face, human behavior, interaction flows. Level 4, application or web systems, full stack web, how apps are structured and shipped. Level 3, distributed and data system, data intensive applications, how big system coordinate, store, sync, tolerate failure. Level 2, operating systems, OS 3 easy pieces, processes, threads, scheduling, virtual memory plus paging, file systems. Level 1, computer organization, inside the machine, instruction execution, caches, pipelines, bus plus physical address space, memory map IO lives here. Level 0, electronics or reality, transistors, voltages, clock edges, signal on traces. Memory map IO is literally the bridge between level 1 and level 0. That's why it feels powerful and grounding. It's the place where abstractions stop and atoms begin. So to directly answer your question, is memory map IO inside the machine? Yes, that's the right category of book, architecture books, not OS or networking. Is OSTEP still real world? Absolutely. It describes very real mechanisms you use every second. It just focuses on memory management, not device wiring. I thought software complexity was already huge. Why is this deeper layer even simpler? Because distributed systems is messy because humans. OS complex because safety plus multi-programming. Hardware boundary surprisingly simple and brutally direct. At the lowest layer, the world becomes put value at address, something real happens, and that's beautiful.